Hey folks, thank you very much for joining me today at Conf42 Python. Today you get to learn about sketching algorithms and how you can make sense of big data in a single pass. My name is Shwe and I'm the VP of Data at Quix. Quix is a remote company and we have teams across Europe and the US and our headquarters in London in the United Kingdom. A bit about myself, I have a background working in high-growth startups as a data engineer and head of data. I help companies determine their data and AI strategy, and where possible, center it around streaming technologies. I'm a big fan of the mantra less is more and simplifying things, because I think that just makes everything easier to build on and maintain. And I'm really interested in the real-time data and AI ecosystem, which should explain why I'm so excited about sketching algorithms. I've put my LinkedIn there in the corner, so feel free to connect. First of all, a bit of information about Quix. So our mission is Python-first stream processing. The streaming data landscape was started and built in Java, and to this day, it's mainly accessible to those who use Java and SQL. The Quix focuses on the Python developer experience, and we have two products. We have Quix Streams, which is an open source library that uses data frames to work with data and build streaming and event-driven applications. And since sketching is based on streaming data, it goes hand in hand naturally with Quix. Quix Cloud is a fully managed platform where you can run your streaming applications and build out real-time data pipelines quickly using open source connectors. We're pushing the idea of streaming data frames, and as you can see, it's reminiscent of the other data frames you may have encountered in Pandas or PySpark. You can build your data transformations using Quix Streams applications, and they're designed to work with Docker and be containerized. You can deploy those containers on your own infrastructure, or if you prefer not to manage infrastructure, you can deploy it on Quix Cloud. We provide a nice interface so you can build out streaming data pipelines. You can get started quickly integrating data with connectors to data sources such as Kafka, MQTT, and databases such as Postgres, as well as popular destinations for data such as Snowflake, Redis, and InfluxDB. The connectors and the transformation code samples are all open source, and we have contributions from our friends and partners such as InfluxDB, and we'd love to have more contributions, so please get in touch if you're interested. So what is a sketch? Note that this is a really large topic because there are families of sketching algorithms all for different use cases, and my hope here is to introduce you to a few of my favorites and inspire you and hopefully get you introduced to the possibilities so you go out and explore by yourselves. After internalizing all the documentation and my experience using sketches, I've come up with this, that sketches are small, stateful, streaming data programs that deal with a huge volume of data, and they provide approximate answers orders of magnitude faster than exact techniques. It's grounded in the truth that when it comes to big data, approximate solutions are favorable over exact solutions because they're a good trade-off for memory, resources, and time. And you might not realize it, but you're already probably accepting of approximations. You may have heard about this little tool called ChatGPT, which works by responding with its best guess, an approximation. And here are some characteristics of sketches. The first is that they're small, and they have to be small, and they're usually only a few kilobytes in size, meaning that they have reduced memory requirements and will grow sublinearly in space. They're stateful, and they maintain a data structure that keeps the state of the observations. So every data point that comes in isn't retained in its exact representation. It's streaming, meaning that it deals with data in a single pass. So the sketch needs to look only at each item in the stream once. And they're fast. They're orders of magnitude faster than exact techniques. The results are also mergeable without a loss in accuracy. That keeps everything fast. And these are the components. So the first typical stage of a sketching process is a transformation that makes the input data stream resemble white noise. So you have a uniform distribution of values. And this is usually achieved by hashing the input keys and then normalizing the result into a fraction, that is, a random number between 0 and 1. The second stage of the sketch is the creation and updating of a data structure that follows a set of rules for compressing down the values it receives from the transform stage. So in the middle there, when you initialize the sketch, you can configure the parameters for the data structure, which enable you to manage its memory. And the last stage there are estimator algorithms that take a query, look it up in the sketch's data structure, and returns a result. Now this result would be an approximate, but the important thing to note is that it will have mathematically proven error distribution bounds. So this helps in dealing with the confidence of the results. So whilst tools like ChatGPT give you an approximation, it's not always transparent about its error thresholds, which is why you get those things called hallucinations. But with sketches, you have mathematically provable error bounds, which helps with confidence that the approximation is sufficient. And let's talk about why being exact is slow. We live in a world where the majority of the time we use exact techniques. And what are exact techniques? It's when you run a query to get the exact answer. For example, a common one I'll go through today is a count of the number of unique identifiers. The most common example is a database query. And hopefully everyone here has experienced a query that runs for a really long time. If you have billions of rows with high cardinality, that is, you have lots of unique identifiers, you could experience a really slow query when you're running a group by count. So distributed systems exist, and they use parallelization to attempt to speed up these queries. And here's an example of how parallelization works to solve a problem such as word count. So on the left there, you have some input data coming in, and to get the unique count of words, count of unique words, it has to go through these stages of splitting the data, mapping, shuffling, and reducing. And these operations happen on different nodes or machines. So each box there represents a node or a separate machine. So splitting and mapping are self-explanatory, but why does it need to go through shuffling and reducing? The reason is because if you look at the mapping step, each of the nodes have local answers, and they are non-additive, meaning that you can't simply sum them up since the same word occurs in multiple nodes. Here you can see that at the mapping step, you can see the word deer and the word bear appear in two different nodes. So shuffling ensures that the same unique words are co-located so that they can be accurately counted. So when the reducer performs the sum operation, you get accurate results there at the end. You get bear is 2, car is 3, deer is 2, river is 2. And this is taken from Hadoop's documentation. And this is common to all massively parallel processing systems such as Spark and Snowflake. And really all distributed databases work in a similar way. And the take-home message here is that shuffling is slow. And when processing queries, you have to do what you can to avoid ad hoc network I/O. And there are techniques in distributed systems like Spark that help you to get around this by using broadcasting, where you would use broadcast joins where you want to join two tables so that rather than a huge amount of shuffling taking place, a copy of the smaller table can be stored upfront alongside the larger table on the same machine, so it's available when the join needs to be performed. And I refer back to the classic notes here of latency numbers that every programmer should know. When you compare the time it takes to read from memory versus reading from disk versus round trips over a network, we're talking orders of magnitude difference. Even though, at certain scale, we're counting things in nanoseconds and milliseconds, when the data gets large and you're dealing with many different unique items, we're talking orders of magnitude difference. So why are sketches fast? There are four main parts of sketching I should go through first. So the first is the stream processor. It processes the data as it streams in with a random algorithmic selection. There's also a data structure, which starts off as an empty summary and is updated with each data point over time as it comes in. The size grows sublinearly. The query processor, it computes the desired result and models the error properties using probability statistics. And lastly, we have merge and set operations. So these are the operations that operate on multiple sketches, and there is no loss in accuracy doing so. Here's an illustration of those four parts. So you have the front-end stream processor that uses a stochastic process to randomly select data, which it uses to populate a data structure. This data structure can be queried at any time using a back-end query processor that has probabilistic analysis to return an approximation with known error thresholds. And at the bottom there, you have a way of dealing with multiple sketches where you can stream them in and perform merge or set operations to combine them into their resulting sketches. And you should note that the sketches are designed to be cross-language compatible as well. The data structures should be easily queryable by the implementation in any language. I used the word sublinear earlier, and what does that mean? So here on the x-axis, we're plotting the number of items or the cardinality, and on the y-axis, it's the memory or the space. So in most data structures that take exact representations of input data, so for example, if you're using words in a key value store, the growth in memory as cardinality goes up is somewhere between linear and superlinear. But with sketches, it's always smaller. So with sketches, it's always sublinear. The mergability I mentioned also keeps things fast. This enables the merging of multiple sketches without loss in accuracy. And this solves non-additive challenges. So I've thrown another term at you, so I'm going to define that too. So what are non-additive challenges? So aside from being absolutely everywhere, let's take this example where Quix has gone into the retail industry. So we've opened up 4 stores in some of the busiest cities in the world. They happen to be the fashion centers of the world. We have the annual sales figures from each store as well as the count of unique products in each store. And with the actual sums of the annual sale figures, since money is additive, you can sum it up to get a global total sum. So you can see we're doing pretty good here. But when it comes to the unique item counts, you can't do this because the last time I checked, the Quix London store definitely has some of the same items as the Quix Paris store. And the Quix Tokyo store has some of the items as the Paris store. So there's usually an overlap. And since that information about unique keys is lost at aggregation time between the stores, you cannot simply sum them up. You would just get incorrect unique counts. But if you use sketches, you could solve this. You could save the sketch for daily records in the database in their own column. Here on the left, we have 2 tables. So one is for all the days in February for the London store, and the one below is all the days in February for the Quix Paris store. We could union the number of days in the month to get the sketches for the unique products per store. Then to get the monthly unique counts, it would be a case of doing a merge on the store's sketches. So here we can combine the sketches from each of the European stores to get a European approximation of uniques. And of course, you could employ data modeling to get the exact unique counts, but that would involve combining data across stores. That's probably a lot of network I/O. And you would have to do this in a batch job. You would wait for all the data to come in and you would perform historical batch. You'd perform it as a historical batch job. So this is a really good example of using sketches where you're able to do approximate analysis with data that is being streamed in and to perform that approximation in real time or near real time. And this is really why mergeability with sketches is such a superpower. So let's have a look at some of my favorite sketches. So the first is counting uniques. So the ones I really like are the ones that estimate count distinct. So there's one called the count min sketch. Also for estimating the cardinality amongst many duplicates. So for that you have hyperloglog and you have compressed probabilistic counting sketches. You also can estimate frequent items. So this is good for recommender systems as well. So when you estimate what are termed the heavy hitters or top K, for example, during Conf42, if we were streaming in the data, we could perform an approximation for what are the top most viewed talks in this conference. We have quantiles and data distributions. So this estimates the distribution. So you've got the different percentiles like 25th percentile, 95th percentile, 99th percentile. You can do all of those with well-defined error bounds. So if you're streaming in data again from this conference, you could determine and approximate how much time people spend on each of the web pages. And lastly, we have sampling. So sampling keeps some semblance of or the transformation of the item from the stream. For example, with reservoir sampling, you choose K samples from a list of N items and you retain that. And to give you an idea of how the algorithms work, I'll cover the count min sketch. Let's start with a naive example, and I'm going to go with food items. So here we're counting, or rather approximating food items. So on the left there, we have a continuous stream of food items coming in. So in practice, this could be food items from orders in an online supermarket or a food delivery service. And on the right, we have a hash or key value data structure, where we're using the key as a representation of the food item, and the value is the incrementing count of the number of times it's observed in the stream. So as we go through the stream one at a time, we're counting this. So by the end, when we get to the last item there, we have counted 1 burger, 3 pizzas, 1 salad, 1 burrito, etc., etc. So this example does only have 10 items, but this approach won't scale at high cardinality. So when there's a huge increase in the number of unique items, it just simply wouldn't scale. So if this stream introduced all the food items in the known universe, the data structure would have to grow linearly or sublinearly this way to hold all the keys. It would mean reserving huge amounts of memory and long wait times when you're querying to retrieve the counts for a food item. And if you wanted this in real time or near real time, forget about it. And from here, there's not much you could do to improve things. Like in a naive way, you could reduce the representation of the food item down to perhaps the first 3 characters. So for example, instead of storing the graphical bitmap, you could save pizza as PIZ, burger becomes BUR, but then eventually as the list got longer and the cardinality increased, you'd start having key collisions, like when a burrito comes along and tries to increment BUR as well. So let's see an example with hashing, which is a better representation of the count min sketch. So in this example, rather than taking the exact representation of the food item, we'll run it through 2 hashing functions. And you can see that there on the right, we've got 2 of the columns, each of which represent the hashing function and the number that they return. And we're going to use this to know how to store it in the data. So it's kind of like encoding a burger as 1 and 6 and storing it in the data structure here in this array in the middle. That way. So we'll use that the hashing functions there on the right to increment the counts in this 2D array in the middle. So this array starts off all blank, or rather all zeros. And the first item in the stream is a burger. So we pass it through to the 2 hashing functions there on the right. And we see for burger, we get the representation of 1 and 6. We then go to the 1 in the first column and increment that by 1. So it goes from 0 to 1. And then we go to 6 in the second column, and we increment that also by 1. Now we have 1 and 1 in those positions. And we're done for this item. So we read the next item in the stream. It's the pizza. We look it up in the right there, and it's encoded as 4 and 1. So we go to positions 4 and 1 in our array in the middle, and we increment at those positions, 4 and 1. So we have a count of 1 and 1. And we'll keep doing that. So we can do that for salad as well. But let's see what happens when a duplicate appears. So when another pizza appears, we look up its hash representation, again, which is 4, 1. And since we already have a count of 1 in each, we increment them again. So now we have the number 2 in both those positions. So you just keep incrementing them by the time you encounter them in the stream. So let's fast forward to the last item. So this is what it looks like when all 10 food items are stored in the array. And now let's try querying the data structure. Now, because it's a stream, you can query it at any point in time. That's the beauty of this. So you can perform an approximation at any time that you like. So let's say at the 10th item mark, we want to query this data structure. We want to get an approximation for the count of burgers. So we look there on the right there, we see the hash representation is 1 and 6. So we look into our data structure in the middle, and we get the counts of 3 and 1. Now, you probably figured out why this sketch is called count min, because we take the minimum value of the obtained counts. So out of 3 and 1, the smaller number is 1. So we have our approximation of a count of 1 for burgers, which in this case matches the exact count. Let's do another example. Do the same with pizza, which has a hash representation of 4, 1. So we look up 4, 1 in the middle data structure, and that gives us a count of 3, 4. And we take the min, so that's an approximate count of 3 for pizza, which again matches the exact count. So you get the idea. You can see that for some of the food items, for example, if you look at the last one there for tacos, that's 6 and 1, which gives us a count in the middle of 1 and 4. So you can see that though we take the min as 1 and our approximation becomes 1, one of its counts got as high as 4. So some errors can start creeping in, like with this particular size. And so this would suggest that you either need to increase the space, making the arrays bigger, or adding more hashing functions. And these are sort of parameters you can control in sketching. So this would all work together to reduce the collisions and keep the counts as accurate as possible. So now that you know what sketches are, how they work, and how useful they are, how do you get started with them today? So you're probably thinking, well, I need to implement them. Like, it sounds like some complex statistics and math going on. Is there anything available in open source? Well, the good news is you'll be glad to hear such a project does exist. So please go and check out the Apache datasketches project. It's available in Java, C++, and you'll be happy to know it's also available in Python. This project was started at Yahoo in 2019, and it achieved Apache's top-level project status in 2021. So it has a really active community, and it's got a good roadmap for implementing sketches. There's a very clear picture of the sketches that have been implemented and the ones that are coming up. And the beauty of this project is that it's cross-language compatible, meaning that you can mix and match languages for different components. So like I mentioned before, with the stream processor, you could implement that in Java. And then the backend query processor could be implemented in Python, and it would all work. But we're at Conf42 Python, so of course we're going to do it all in Python. And I'm going to do that here. So I'm going to use these final few slides to show you some code in Python. So this is an example in a Jupyter notebook where I load in some Spotify data and filter it for the artist information. So you see I've imported in the library there, and I've also imported in pandas to load in the data, so they're interoperable. You can see there at the bottom there that I've specified a confidence score that I want, which is a percentage. So I want 90% confidence. And you see that the library gives you some convenience functions that helps you get a suggestion for the number of hashes you should be using to get that level of confidence. And the same again for the relative error, which I'm going for 1%. It will suggest the number of buckets that you want to instantiate this count min sketch with. And to make it easier to follow, you'll see that I load in the records one at a time using a loop. So when you run it with such a large data source as the Spotify data that I'm using, it actually takes a while. And in reality, what you'd be doing is you'd be reading the records one at a time from a stream and then updating the sketch that way. So for that, you could use Kafka with quix for this because it's sort of a general purpose use case. But if your use case was something else, like getting approximation statistics like quantiles and counts from changes that are happening in one of your databases, you could use change data capture with something like Debezium to obtain a stream of changes, and then you perform the updates in that way. So getting into a stream is really the first part of the puzzle there. You can see the sketches provide functions there which allow you to specify different things there. You've got a lovely print statement there that shows you what the sketch summary is with their number of hashes, the number of buckets, the number of filled bins, etc. So this is a good way for you to keep an eye on how you should size out your sketches. So yeah, you can see they provide They maintain the desired confidence score. You've got nice summaries, and at the end you can see I've put in the estimations. I've requested the estimations for some of the popular artists in that data source. And this one's my last slide. So you can pip install the Python library today and get started. You may already even have sketching algorithms available to you if you use certain database technologies or processing engines. So we have Druid, we have Postgres and Hive, which have been supported for some years. And it's been implemented recently in Apache Pinot and Apache Spark last year as well. So if you're using any of these, you should be able to just search for in the documentation the sketching algorithms available, and a lot of them will have things like hyperlog and some sort of counting or quantile operation. They should have those. So as I mentioned, there is an active community of mathematicians, data scientists, and engineers working on sketches. So you'd be amongst really good company if you do check out the project and want to contribute. And so, yes, I'm certainly going to be exploring more sketches in future, but I'm curious to know how you'll get on as well. So please do let me know what you think. Here are the links to the QuickStreams open source library in GitHub, where you can start the project to follow its process and follow its progress, and most importantly, show us your support. And also, please do come hang out with me and the rest of the Python team in the Quix community on Slack. And we'd love nothing more than to help you get started with streaming data using Python today. So if you're going to implement the sketching algorithms and you don't know where to start, please join us there. So thank you very much for taking the time to join me today, and I hope to see you soon. Peace out.